Hello everyone, I'm going to try and start posting videos more frequently from now on, and these videos are going to be called Daily Physics. And the idea is that each video gives you a bite-sized piece of physics which covers in its entirety a complete course. And the course we're going to start with is thermal physics, that is Thermodynamics and Statistical Mechanics. And it's a really satisfying piece of physics to learn because in thermal physics you start from the laws of thermodynamics, these really simple laws, and from there you build up this enormous picture of great complexity, and it's really satisfying to do, and there's great beauty in it. In fact, it was Albert Einstein's favourite branch of physics for this very reason. Now, the first thing we have to talk about when it comes to thermal physics is that in thermal physics we are dealing with very large numbers. Now, we have large numbers in our everyday lives, right? So, for example, a YouTube video might get 1 million views, probably not this one. 1 million is 10 to the power of 6, or the number of people on Earth is of the order of billions, that is 10 to the power of 9. But these numbers pale into insignificance with the kind of numbers we're talking about in thermal physics. So an average piece of matter is made up of atoms, and the number of atoms is of the order of 10 to the 20 something, right? Now that is a vast number of atoms. And if we are trying to make predictions about how this system behaves, if we wanted to do it what's called like the brute force way, where we say, right, let's make an assumption for each atom about its position and its momentum at any one time, and then do that for all the atoms, that is totally infeasible, right? Because you'd have to have like a computer running for the age of the universe before you even got a single prediction out of it. So what we need in thermal physics is a way of making aggregates, making averages, and using this for such large systems to make predictions about what we're going to see. And that's exactly what we're going to do, and in future videos we will see some statistical and probabilistic methods. But the first thing we need to do is recap, or indeed go over, what a mole is, because this is a number that's going to come up again and again and again. And once we've got an idea of what a mole is, then we are going to talk about the thermodynamic limit and give an idea of why it's important to make these kind of aggregates in order to make predictions. So what is a mole? Well, a mole is an amount of whatever stuff we're dealing with, right? So if I hold up a block of matter and you say how much stuff is in there, I go, well, I've got about 12 moles of matter here. And how a mole is defined is that 1 mole is the number of atoms in exactly 12 grams of carbon-12. That is the isotope of carbon with a molar mass of 12, 6 protons and 6 neutrons in its nucleus. And the number of atoms in 12 grams of carbon-12 is equal to the Avogadro number. So that's another term that's going to come up a lot. Now the Avogadro number we write as n subscript a, and that is equal to, let me just make sure I get this right, 6.022 times 10 to the power of 23. So the number of atoms in 12 grams of carbon-12 is equal to the Avogadro number, which is 6.022 times 10 to the 23. And that is what a mole is, right? So you'll also notice that when I gave the definition of the mole, I said it's the number of objects. So if we have 1 mole of hydrogen molecules, H2, then that is 6.022 times 10 to the 23 H2 molecules, right? It's not 6.022 times 10 to the 23 H atoms, right? Because if we were dealing with, that would be half a mole of H2 molecules, right? So it's the amount of objects which is equal to the number of atoms in 12 grams of carbon-12. Now that might sound a little confusing at first, but really this is the number you have to remember. It's the Avogadro's number. And as you can see, it is absolutely vast. And whenever we're dealing with matter, this is the kind of scale we're dealing with. So there's one other thing we briefly need to cover while we're here, and that is the molar mass. And as you might expect, the molar mass is defined as the mass of exactly 1 mole of the substance. Now, since we defined the mole as the number of atoms in 12 grams of carbon-12, the Avogadro number, it should be no surprise that the mass of 1 mole of carbon-12 is 12 grams. But more generally, if we're trying to find the molar mass, what we need to do is take the Avogadro number, that is the number of atoms in our mole, and we need to multiply that by little m, which is the mass of exactly 1 atom or 1 molecule or whatever it is which we're trying to find the molar mass of. So now we have gone over what a mole is, we're going to finish this short video by looking at what the thermodynamic limit is and why that's so important. And we're going to do that by means of an analogy. So let's imagine you're sitting in a tiny hut with a tin roof, right? And it starts to rain. And whenever a drop of water hits the tin roof, it exerts a little force on that tin roof. And what you're going to do, or what you want to do, is to measure the average force over time on the roof, right? So here you have force, and here you have time. And what you notice is there's no force when no raindrops are hitting, and then 1 raindrop hits there, and then nothing, 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 and then another one hits, and then nothing, nothing, and then another one hits. There we go, like that, right? Very small roof, you only get occasional raindrops hitting, and when that raindrop hits, this is the average force over the entire roof. So you get these big fluctuations because you're only getting a raindrop every now and then. Now let's imagine that you have a much, much bigger roof, right? So now, when we're measuring the force over time, we're getting much more frequent raindrops, right? So we're looking at something like this. Still more fluctuations, but really it's much more regular, the average force on the roof, because we've got a much bigger roof. Now, if we take an enormous roof, the biggest roof we can possibly think of, then we get this effect, but even more so, right? There's a raindrop all the time, and now when we're measuring the average force, it's almost exactly a straight line. And this is the idea with the thermodynamic limit. The point is that the more raindrops we're dealing with, the bigger our system is, the more these random almost fluctuations average out to give very predictable behavior. And what we can do is make predictions about this very predictable behavior without having to make individual predictions about every single raindrop or every single atom in our system. It's simply not necessary anymore, because when we have such vast systems, when we have 10 to the 50 raindrops instead of just 3, then the behavior becomes extremely predictable. And this is what we're doing in thermodynamics, right? Because in thermodynamics, we might have, say, a box of some sort of nitrogen gas or some other gas. And if we want to know the pressure on one side of the box, that is exactly equivalent to this situation, because the pressure is defined by every time a molecule or an atom hits that side of the box, it exerts a force. So if you only had 3 or 4 molecules or atoms in that box, you would get this kind of behavior. The pressure would be 0 most of the time, and then suddenly you'd get these little pings of pressure. But because you have vast numbers, because you have numbers of atoms on the scale of Avogadro's number, on the scale of moles, then the pressure on the side of the box is essentially constant. It's a flat line, and that is the point. Okay, well, that's done as an introduction. In the next video, we're going to look at the ideal gas law and how that was derived, and then we might even get to start doing some worked questions and examples, which will be fun.